We close section 8.2 with example 2, which is actually a reproduction of example 8.5 in your textbook. On the left side of the figure in part A, we have a beam of length L subjected to a uniform distributed load of strength W0. On the right side of the figure in part B, we have a beam of length L subjected to a single discrete force P whose magnitude also happens to be equal to W0L. We are first asked if the two loads are equivalent. The answer is yes, and it should be clear why. If we were converting the distributed load into an equivalent discrete load, the magnitude of the discrete load would be W0L, and its effective center would be at L over 2. P has the correct magnitude and position to be equivalent. We are then asked if the shear force and bending moment distributions are the same for both loadings. The answer turns out to be no, and this reveals a shortcoming in our equivalent force systems principles. Strictly speaking, equivalent force systems are a concept applicable to rigid bodies, not deformable bodies. If we think back to the exaggerated deformations we introduced at the beginning of this topic, we had the following. We had two coupons of material, the one on the left subjected to a shear force distribution, and the one on the right subjected to bending moments. And we said that under these loads, the original undeformed coupons would tend to turn into these sorts of deformed bodies. Different shear and bending moment distributions give rise to different flex and different peak deflections. This deficiency in applying equivalent force systems to deformable bodies is also why it's crucial to keep distributed loads intact in our equilibrium approach until after we've made the cut through the rigid body. You should consult example 8.5 now to see the derivation of the expressions for shear force and bending moment for these two cases. The results are reproduced below to facilitate additional discussion. For P equals W0L, we get the plots below. A couple of issues merit discussion. Note that, once again, the peak and the bending moment distribution coincides with the location where V goes to 0. This isn't just a coincidence, and we'll be discussing it further in section 8.3. For P equals W0L, the bending moment distribution has a piecewise linear sawtooth shape, and it peaks at twice the value of the bending moment distribution for the parabolic shape associated with the uniformly distributed load. Without knowing anything yet about the mechanics of deformable bodies, it is still possible to tell which of these two loadings produces the larger deflection. The supports at A and B are meant to convey no vertical deflection. Both beams flex under their applied loads. The beam with a discrete load has 100% of its applied load applied as far as possible from the vertical supports. In contrast, some of the distributed load is applied as far away as possible from the supports, but some of it is applied near the supports. The case with a discrete load produces a larger peak deflection. Even though the peak bending moment in case B is 2 times that in case A, it isn't the case that the peak deflection in case B is 2 times that in case A. For that, we really do need an approach rooted in the mechanics of deformable bodies, and it will turn out that for the support shown here, the peak deflection in case B is about 60% larger than that for case A. In conclusion, shear force and bending moment distributions have to be obtained for actual rather than equivalent loadings because the distributions differ between actual and equivalent loadings, and those differences result in different peak deflections.